system when the buses are starting to take out from their right position. And this is what we did in Santiago. So regarding bus bunching, this is a severe problem if it's not controlled for many reasons. First, most passengers wait longer than they should for a very crowded buses. Second, it reduces reliability, affecting passengers that they don't know how long it will take. Sometimes it's 2 minutes, sometimes it's 5 minutes, sometimes it's 12 minutes. In average, maybe 3. And also operators that they don't know how long will the bus take the whole cycle time. And therefore, they need extra buses and extra drivers to have a smooth operation. So it affects cycle time and capacity. And very important, because passengers wait longer than they should for crowded buses, people start complaining there's obviously not enough buses. So it puts pressure in the authority for more buses. So the contribution here is to have a control mechanism to avoid bus bunching, and that's what we did. What we did was to create a control mechanism which is based on real-time information or estimations about where buses are, based on AVL, how loaded buses are, and you know the trajectory of the bus, so that you can have an estimation of how crowded the bus is, and how many passengers should be waiting at each stop, based on when was the last time a bus visited the stop. And with this, we run what we call a rolling horizon optimization model. Each time a bus reaches a stop, or every certain amount of time, for instance, every 2 minutes. And the model, what it does, it minimizes the waiting time for the first bus of everyone, the waiting time for subsequent buses, if the one you cannot board because it's full, and also the time people being held inside the bus. Because the control mechanism we will be implementing is holding buses. When do you hold the bus, for how long? But here we have a little animation for those of you that have seen it many times. Bear with me, but I have to do this.
One of my favorite movies.
Okay, fine. So what I have here is the same corridor. The squares are the stops, the circles are the buses. We have 30 stops, 15 buses. The color of the bus means it illustrates how loaded is the bus. Green being not very loaded, red being very, very loaded. And what you will see for 15 minutes is that nothing will happen upstairs in the upper simulation and the bottom one. And after 15 minutes, I will start controlling the bottom one, and this is what you will see. So I try to make it as fast as possible because we have little time. There you go. You have our buses. Do you see our buses? They are starting to bunch. So here you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here you have 2 together, for instance. And when we reach 15, you'll see how on the bottom one, we haven't done anything here, we'll start holding buses to prevent them from bunching. So take a look at what will happen at min 15 and what will happen from then on. So here nothing has happened. Look at the bottom. Whoop, we hold it. Yeah, you held it, and now from now on you can see how on the top, this is what a regular corridor usually looks like, and this is what it should look like if you were to intervene properly. And what you see is that this is closer to what a metro line performs, and this is closer to what we see everywhere in the world about our operation of the bus, how our buses operate. And no wonder why people say, well, I prefer metro. I prefer metro. So the question here is, how can we intervene our bus corridors to have them performing this way and not that way? Okay? So the simulation bias results, I won't show you the result because I've shown them many, many times. If you're interested, they're in the website. But as a summary, what we show with this simulation is that you can reduce excess waiting time. And by excess waiting time, I mean everything that is over what you cannot avoid. If you're running 30 buses per hour, there's no way you're going to have an interval in average that is lower than 2 minutes, so everybody will wait 1 minute at the best. So here we're talking about everything over that first minute. We can reduce it in about 60%, where excess waiting time can drop in 80%, and waiting for subsequent buses, you can drop it by 90%. Also, of course, comfort is improved significantly, and reliability for users, it's also improved significantly. What we have here is that if you have an average interval of 2 minutes, people waiting twice the average interval or more will drop from 1 every 9 trips, 1 every 11 trips, to 1 every 1,250 trips. So it's really much more reliable. And interestingly, even though we are holding buses, the average cycle time drops by 4%. That's an extra capacity that you win. And also the variability of the cycle times drops by 35%. So
less fleet.
yes, so this is the opportunity. And this is what we're doing. So what we did then, and this is something new from those of you that were here last year, we looked at what would happen if some of your drivers would not obey your orders. What if you have drivers that say, I don't care, right? As the guy in charge of the New York system told me. There's no way I can pass orders to my drivers. And what you see is that if the obedience rate, this is what it is 100%, this is the amount of your saving. Now, if the percentage of obedience start dropping, well, the saving starts getting reduced and reduced, of course. This is what we observe. But there's a safe 20% when really nothing happens. If 20% of the time a driver will not obey your orders, nothing happens. As long as it's a random disorder. It's like every driver has a probability of 80% of obeying your order. It's not just the same guy that is all the time boycotting your system. If that's the case, this is what will happen. So if you have drivers boycotting, that has an immediate effect. Immediate effect. So it doesn't matter if your signal doesn't reach the driver 20% of the time. No problem. However, if you have 20% of your drivers deciding to boycott your system, it will have a significant effect. So this means...
And you know which drivers they are.
This means you need to record what the drivers are doing and have a correct incentive for them to obey what you're saying. Basically, what you're saying is you cannot start until the light turns green. If it starts early, well, that's a problem for him and for you. So now let me tell you about a little implementation we performed in Santiago, because we wanted to see if this that works so well in the computer would work as well in the streets. So what we did was to take one bus corridor in Santiago and try to control it from 7 a.m. to 9:30 a.m. We chose, out of the 130 stops, we chose 24 of them. And we put one person in each of these 24 stops to receive text messages from the computer telling them the order of if he should hold the bus, yes or no, and for how long. Basically, they gave him a time in which the bus should leave the stop. So this is the situation. Here we have the person taking the notes and communicating to the driver. This is the corridor. It's pretty long. I don't remember how long it is. Long. He's south of the city and going downtown.
70 stops each way.
Huh?
Each direction has like 70 stops.
Okay. So it's probably, I don't know, 15 kilometers each, 15 maybe. And the results were very promising, even though the conditions were far from ideal. The AVL location unfortunately didn't work very well that day, and instead of receiving this information, what we received was this information regarding the position of the buses. So of course, it definitely hurts your results, right? But anyway, the results were good. So we can do much better if instead of receiving this, we would receive that. And now I'm going to show you the trajectories on this is what happened on our day, and this would be any day. So you can see, for instance, if you focus here on the bottom part, how the regularity improved, and I will show you, for instance, in terms of the indicators, the incentive that the authority have for the operators. They looked at how many intervals were longer than twice the interval. For instance, if the average interval should be 2 minutes, they looked at how many intervals were 4 minutes or longer. And for every minute over the 4 minutes, they would pay a penalty. And on that particular day, we were able to reduce the penalty in comparison to the average penalty around half, which is it's very significant. And we think that if we were to get better data, we could double it completely. Another thing that happened, which is interesting, is that on that particular day, because they were running more evenly spaced buses, they were able to have a higher demand. This is a plot where in the x-axis where they have the demand for the line we were controlling, and on the y-axis they have the demand on all lines of the system. And you can see, of course, that when the whole city was having more demand, the line 210 was getting more demand. So that's the clear correlation. The day we control is over here, meaning that all the lines were performing at a low level. However, the 210, the line we were controlling, outperformed. So if you have your buses evenly spaced, you will attract more demand just because your supply, even in the short term, your supply will go evenly spaced. If you have two buses coming together, you're losing your supply in some sense. So we think that the pilot plant can improve significantly because we can have better GPS data, of course, because we can run the optimization model more often. We were running every 3.5 minutes. We can drop to 2 minutes, and our prediction will be much better. We can calibrate better our speeds and our arrival rates. This was the first time, only for like a one-time shot. We can do much better. And we can also check the data inputs before feeding the system. And that's what we're working on. And most important of all, we can bypass the person at the stop, which is very expensive, and communicate directly to drivers. But that forces us to think of a device to be implemented at one side of the driver, telling him what to do directly. And this is what we're going to do. So we developed this tool for headway control using holding in real time, reaching time savings of over 50%. These time savings can be extended significantly if we were to incorporate, for instance, traffic signal priority, for example, or other type of control measures that we could add. The improvements also in comfort and reliability are very promising. And the tool that we have developed is fast enough for real-time applications, as the example we implemented show. Finally, we've been able to publish some papers here. We have with Ricardo and Felipe. The last one is coming in Transportation Research this year. Okay? We also have developed, which is interesting, because sometimes these ideas are hard to communicate because they're not as intuitive, and not as intuitive that this is a hard problem. So we have developed a game for people to play, to say, okay, you think this is easy, why don't you try to control yourself with your intuition by looking at the buses, and if you want to take a look, it's going to be here, so you can play if you want. Huh? So there's a little game for you to play and try to control buses and see how you perform. Finally,
you're saying the computers are
huh?
there.
Sorry?
So you're saying the computers are there.
Yes, you're the guy in there saying the last bus passed us 3 minutes, the next one is coming in 4 minutes. What do you do? Basically. Yeah, basically. Yeah. Try to be a sapo. And the final thing, yesterday we submitted a proposal to an innovation grant in Chile for 500 grants. 40% of each, which was committed by a bus operator, the same operator of this bus. They said, okay, we're going to put $200,000 if we get it. And then the $300,000 will be given by the government if we win this thing. Huh? But this is what we did yesterday, and the goal is to turn this experience into a commercial tool. So eventually to something that you can implement worldwide. This is the goal. Huh? For a detailed talk, because I had to make it into a very short time, you can go to brt.cl. This is a webinar I gave in mid-December. That's it. Question? Yes?
Just curious, how the passengers respond to this kind of control strategies. I mean, the obedience rate for the drivers is clearly critical for the success of this control. But how the the obedience of the passengers is also important, because if you hold a bus, based on your study, it might be benefit to the passengers, but they probably don't perceive it like that. So
well, I think there's many things here. First, passengers complain much more about waiting than staying inside the vehicle. Second, you need to implement this in a way that is not as it's not as obvious, it's not as dramatic. So for instance, we never held the bus more than 1 minute. And if you can do this very frequently, you can have 20 seconds here, maybe 30 seconds at the next stop. So you can handle it in a more smooth way, so that the passengers don't really realize. And always bear in mind that waiting is much worse for the passenger than holding inside the bus. And the other thing is that we're going to be holding buses way before they bunch. Because we're looking at buses at the whole corridor at the same time. So it's not that we're going to hold the bus that will be that has already bunched. Pilar and Chris.
Yes,
And then Ricardo.
why did you only hold that 24 out of 130 stops? Was it because of computing?
No, because it was too
capability or
expensive.
People.
People, it was so for us it was very expensive, and it was good enough. We made some simulation and it showed with 24 we were safe. Chris?
Is there any evidence that providing information to the passengers will help? So, you know, we've all been on the metro when it's stuck, and you're like, why is it stuck? And like, some of us know it's probably control strategy, but, you know, is there a way that is there any evidence that suggests when the passenger informed why the bus is stopped, it might improve the passenger?
Could be. I think that's a very nice question. I always thought that if you were to communicate to the users why you're doing the things you're doing, it would be much better received. I think. So if you were to say, look, this is our commitment. Yeah. This is a bus service that used to be very unreliable. This is what we will do, and our promise is that this is the level of service that you will perceive
That will
now.
probably need to be part of your business strategy and your
Sure.
commercialization.
This is very similar to ramp metering 20 years ago. Same thing. Why is it better for me to wait at an interchange
Sure.
than to get right onto the freeway? Why am I better off?
And how was it communicated? Was it
Well,
sometimes?
highway engineers were in charge. So what's the
Why
answer?
should, that was not communicated.
Ricardo, Laura, John.
No, I just wanted to add the same thing, and actually the analogy with RAM metering is perfect. We are doing exactly the same. We were trying to keep the system working, and that, but to do that we need to hold some buses on some key intersections.
Laurel, John comes.
But in answer to Chris's question, we are thinking about doing a before and after survey of passengers to see if they even notice.
John, Carlos, Brendan.
When do you, if you're going to tell the driver, I mean, you showed the guys at the stop, so he's obviously saying hold or go.
Yep.
If you're going to tell the driver, you could lessen this if you could give him a little bit of advance notice if he's going to have to hold at the next stop, because then he could kind of slow down. And you know, the question is there some way to lessen the actual hold by giving him this advice?
It makes sense. Makes sense.
Yeah.
The bad side of that is that the people inside the bus will take a little bit longer to reach the station. Or the other thing you can do is, instead of holding, say, drive slowly to the next one, right? But if you do that, people arriving to a stop will be forced to take the next one. I mean, I think it's better to have it unless you're making it unbearable, or unless you really are causing a local problem. It would be better to have it there, so that if somebody arrives and can take the bus, it would be great. So Carlos, Brendan, Amit. Okay.
Hi, my name is Joaquim.
Oh, sorry, Joaquim. So that's what you said, Carlos.
I work for transport department in Rio, the next city to host the Olympics. So you know we have a big challenge in terms of mobility, and I'm very curious about. I don't know if you guys know, we have an operations center. It's the most high-tech operations center in the world. It's a partnership with IBM, so we centralize all the information to the different transits. So, in my opinion, in the opinion of the mayor, does it make sense to have a smart city only for the Olympic Committee and for the city hall? We have to spread the message for the citizens. So I just wonder if we can use this kind of system. We are launching the next month an application, an app that you can download on your smartphone or on your iPhone to share the information when the next bus is coming.
Yeah.
Do you think we can use it?
Absolutely, yeah. What you're saying is part of the project. Part of the project would be not only to be able to make a package for the software, but also be able to provide this information for the managers or the people that have to look at the system and see what's going on, and also for the users regarding what's going to happen when the next bus will come. So definitely, yeah. Somebody else was on Brendan?
2 points. First, this is extremely important work.
Uh-huh.
The question then is how do we make it actually work in practice? I think we come back to operations management philosophy. I know I keep on banging that same drum. It's one of two approaches. It's either problem responsive, problems happen, you fix them, or you control it. Now, up to now, in most places we're working within the city streets, you don't have control over your environment.
Yeah.
In BRT you do. Sometimes you have 100% control, sometimes somewhat less. I think we're able to move into the realm where we control the environment, and you use something like this as, okay, it's the final solving. You take a look at how air traffic control works. They don't wait until the planes are bunched on the approach in and think, ooh, better do something about that now. Or similarly, the way a production line works. A thing should be in a particular place at a particular time, and you control and you design your environment so things are where they should be at the time. Then you have sensors that tell you when things are slightly out of position, and you respond in that way. And that's where your detection and management system comes. But I think we need to look at a totally different philosophy to operations management, where it's not fix it after it starts to break, but determine where it should be and manage that it's in the right place all the time. And one of the places that really flows back is where we talked about earlier, the traffic signal priority, and also in how we manage the movement of people within the stations. Secondly, just on in feedback to drivers, there's a huge number of devices in Europe and Korea and various others which are already providing a very large amount of information to the driver on where they are relative to other buses or relative to their scheduled time. So the devices are already there, and I suggest better to use something that's already in the marketplace than to try and develop something from scratch.
Okay, good. Yeah, the idea of working with the passengers is interesting too. How many passengers do you want in the station really? And that is particularly interesting for those systems that are reaching capacity. For instance, in the case of Bogota, Transmilenio, for me it's quite evident that what you have to do is to hold back a little bit your passengers so that the number of passengers that are at the station are exactly the ones that will be able to board. Because otherwise, all they do is to press people more and make it more comfortable and make operations worse. Ariel?
I just had a quick question on the graph you showed with the capacity of your line after control. Was that still saturated, or did you manage to bring it all the way down to the point that people are not waiting for a second but all get into
In the simulation?
Yeah.
Because the result was a simulation. In the simulation, what we show is that if you don't do nothing, if you don't control, what will happen is that some buses, not all, will reach capacity. And we'll have a very terrible level of service in that sense, being very slow and damaging the level of service offered. However, if you control, very few buses, if any, will reach that level of saturation. So that's why we claim that it can allow you to improve comfort.
Going along the same line, I mean, the bunching often happens that one bus becomes overloaded, it falls more and more behind, people slower loading, unload, the other buses come behind, and have a train of buses. So what you really would like to do is that the first bus go faster. Now we're talking about holding buses. Are you also considering ways of accelerating buses?
That's a very interesting question. It's that's how we started. It's such a pity that for controlling, we're controlling by delaying. Why wouldn't we be able to control by accelerating? So in the dissertation of Felipe, we had two control tools. There's one thing you can do is, well, what if we overpass buses? And it's not very helpful. It's not very helpful. What would be helpful because the bus you need to speed up is not the one that is behind, it's the one that is full. Yeah. And the problem with the bus that is full, that is stopping all the time. Exactly. So what we're trying to do is what we think we should do is try to prevent people from boarding the bus that is already full. And that forces you to say, you know what? There's 2 or 3 spots in this bus already. You could board it, but it's already very crowded. It's very late, and the one that you will board is about to arrive. So and there are some metros in the world, for instance, Sao Paulo, that do that. And I think, but I'm not sure if they do it through intuition or with some proper models telling you this is the number of passengers that you need at the station.